G'day everyone, welcome to our second webinar for 2017. My name is Reuben. I'm the Managing Director of Papworth Construction Testing Equipment, or PCTE. Those of you who are not familiar with us, we sell a range of testing equipment here in Australia and also in New Zealand. We have offices in Sydney, Melbourne, Brisbane, Auckland and also Perth. The types of equipment that we sell are non-destructive testing equipment. We also sell lab testing equipment for soils, aggregates, concrete and cements, and we also sell ground penetrating radar and then also geotechnical instrumentation. And in terms of upcoming marketing events, I'll just take this chance to tell you a little bit about the ones that we've got coming up. We have the Concrete Institute of Australia conference exhibition that will be held in Adelaide in October. We also have the New Zealand Concrete Conference, which will be in October, that's in Wellington. We also have the No Dig, which is a utility location exhibition that will be held on the Gold Coast in September. And then we also have the Australasian Corrosion Association exhibition, which will be held in Sydney during the month of November. In terms of future training offerings, we've also got a ProSec seminar, which is a biannual event that we've been doing for quite a few years. For those of you who have joined us before, you'll know that it's quite a hands-on type of experience where we give you a lot of experience with the equipment and get you to do testing blocks. We also have some visitors coming from Switzerland from ProSec who will be supporting us with that particular event. And we also always offer our own personal training, so we can cater any training course to your company's needs, either whether that's with the purchase of a new piece of equipment for a rental or just for general training purposes. On our YouTube video, we have new content coming up all the time, whether they're training videos. If you have a request for a training video that you'd like for us to add to it, then that would be great. And also we've got an upcoming GPR video, which will be coming from Stuart in Melbourne. He's done a really good comparison between two of our utility location products. So today's webinar is going to be on the subject of early age strength for concrete. First, we're going to have a bit of an introduction into the theory of measuring early age strength. We're also going to have some practical notes on the techniques, and then we're also going to have a bit of an overview on the Australian and New Zealand standards and how they relate to this particular subject also. Some of the products that we'll be talking about today will be the IntelliRock range, so that they have their maturity systems, but then they also have their match temperature curing systems. So if you'd just like to watch this little video, with match temperature curing, we can match the temperature of the concrete to a curing tank, and therefore we can better match the concrete strengths that we get in the lab. This allows us to get higher strengths because the concrete at higher temperatures cures faster, and overall allows us to do projects much faster and to keep the cost down. So this is one of the subjects that we'll be talking about with you today, and we've just actually delivered one of our first systems out to a site in Sydney. So without further ado, I'd like to introduce Mr. William Ward. He's our New South Wales and NDT manager. He'll be talking about the subject. He's got some great experience, and so therefore, take it away, William. Thank you.
And welcome. Thank you very much for joining me today. Now, we are live now, so if you do have some questions, on the right-hand side of your video, there's the live chat option. Please feel free to communicate with me that way. We're on a short lag, so if you send me a mention or something, it'll take me a little while to see it. So today's topic is going to be early age strength, and I'm going to begin by talking a little bit about some definitions, what I mean by early age strength, what we mean by concrete strength. I'm going to talk a little bit about why we would want to measure the early age strength of concrete rather than 28-day strength. I'm going to give a quick summary of methods and start comparing them so you can understand why you would use, say, maturity testing over a early age cylinder break and why and the different methods of curing those. And I'm going to go into detail on each technique, just quickly explaining them and what they're used for. And then once we've completed the overview, I'm going to go a little bit more deeply into some of the standards used for early age strength. In particular, I'm going to go through the American Standard for Maturity. So the definition of early age strength I'm going to be using is a way to measure the current compressive strength of an in situ concrete element before the 28 days compressive strength testing is complete. By compressive strength testing, I'm going to be going off the Australian standard, ASTM 12.9. So why do we want to measure the early age strength? It's going to give us an immediate measure of what that concrete element is doing, and that can be used for decision making, whether that's to know that strength has been gained and continue schedule. This is very commonly what an early age concrete cylinder is used for. We break it 1 day or 2 days, and then we choose based upon that break what the next step will be. It can also be used to improve safety if you have a series of cold days and the cylinders in their 23 degrees centigrade are curing along nicely, providing a certain strength, but the concrete on site is really not getting the same curing environment. Is that going to relate to each other? And it's going to give the people making decisions on is it safe to take action more information to do so. It's also very common to use early age strength information to decide when to apply initial and final stressing of post-tensioning. So there's going to be two different forms of early age strength measurement I'd like to discuss. The first of those that rely upon a conventional cylinder test, where it'll be broken and that'll give a direct measure of the compressive strength of that sample. And it's how we treat that sample that helps it relate to the early age strength of the concrete. The other measurement methods I'm going to discuss are going to be methods that are correlating another measurement. It might be the rebound index of a Schmidt hammer, or it might be the time temperature history provided by a maturity meter. Either way, we take that measurement that is not strength and we relate it back to strength and use that to inform information. So each of these techniques are suitable for certain tasks. Sorry, 1 second. These tasks are going to depend upon how and when we want to measure, and if we want the ability to repeat the measurement. So, a particular characteristic of the techniques that rely upon a cylinder break, the cylinder testing or co-location or match temperature curing methods, is that it can't be repeated. If you have a cylinder which has been cured in a certain environment to represent the early age strength, and we break it, we can't break it a second time. It may be we have a second sample and we can break that, but then we've got to repeat the costs and requirements of that test. Whereas the in situ tests, whether it be taking Schmidt hammer tests off the results or the use of temperature sensors to measure maturity, we can check those periodically. We might come back 2 hours after an insufficient strength has been measured and repeat the measurement at no additional requirement. The second thing is, if we're breaking cylinders, we get our results directly in compressive strength units, MPa. Whereas if we're using a coal-layered method, we need to convert another index to that. And finally, I'm going to talk a little bit more about the qualities of the comparisons and this as we go forward, but I wanted to begin by really highlighting the difference between the two techniques. So, beginning with cylinder strength testing, the most common and still used method is an early age cylinder, which is cured just like a conventional cylinder, but is then broken earlier than 28 days, according to the appropriate Australian or international standards. Everything else, which is a cylinder strength test, is an attempt to improve the relationship of these cylinders. So curing them differently or placing them out in the field with the samples or the real environment to appropriately, to better match the curing environment of those samples to the concrete. So the standards relevant here, AS10 12.8 and 10 12.9, cover how to correctly cast a cylinder and how to correctly break that cylinder. The New Zealand standard 3112 part 2 mentions the same thing. It's the procedure for casting and breaking cylinders. Interestingly, the New Zealand standard already mentions co-location, in that one of the possible curing environments is to protect those cylinders to prevent loss of moisture and to place them out in the field with the element being cast. I'm also going to bring up a little bit ASTM 12.19. This standard doesn't relate directly to early aid strength, but what it does relate to is how to protect cylinders where we raise the temperature of that curing bath. And I think that's important when we later discuss match temperature curing. So, back to our comparison of techniques. Early aid cylinder strengths, which are a conventionally cured cylinder, 28 days. 28 days, not as a 28-day cylinder would be, but we're going to break it early. So there's not much additional setup requirement. The cylinder is simply needed to be cast in addition to the 28-day cylinders and broken early. The relationship, it's the same kind of sample as used for 28-day strength, so it's going to be there, it's going to be useful, but it may be that if the element is curing more quickly due to increased heat of hydration, we're not going to capture that additional strength gain. Now, if we take cylinders and we try and cast them in the same place, we're going to be maybe capturing the real temperature of the curing environment, hot or cold. So this could improve our relationship if it's done correctly, but if we've made a poor attempt to co-locate, maybe it doesn't correctly capture what's happening. Again, very low setup requirements. Finally, match temperature curing is going to be an attempt to capture the real internal temperature of the concrete and create a curing environment artificially to match that. So when the cylinders are placed into that environment, they have the same temperature as the internal concrete. So 10.12.8 and 10.12.9 cover casting, curing, preparing and breaking cylinders. When they're cast, it's commonly that they would be a 100 or 150 millimeter diameter cylindrical sample with a 1:2 ratio. These samples must be compacted appropriately. To do that, they may be rodded. An external vibrating table may be used, or an internal vibrator may be used to compact the concrete. A corner case here is also that self-compacting concrete is just placed into the mould, allowed to compact, and air bubbles knocked out. The key thing here is that external vibration can be used for any slump flow properties, but when it's appropriate to use rodding or internal vibration is going to be partially controlled by that slump index or other factors that affect the compactability of that concrete. So when choosing how to prepare the cylinder on site, an appropriate method of compaction must be used. If we don't compact the cylinder correctly, it's not going to correctly represent our strength no matter how we cure it or break it. Finally, the Australian standard does define that those cylinders need to be covered to prevent loss of moisture. The curing environments in Australia are defined by where in the country we are. In the temperate zone, it's a 23 degrees centigrade curing environment, and in the tropical areas, it's a 27 degrees standard curing environment. And the other thing that's defined here is that there's an initial curing period, minimum 18 hours, no more than 36 hours, where the cylinder is cured inside its mould, covered to protect from moisture loss, but not in a moist or immersed environment. Once that period is complete, the cylinder needs to be transferred as quickly as is practicable into a moist curing environment. A quick note here is that the Queensland Transport and Main Roads test methods require wet storage of the samples immediately, or where it's a steam cured concrete element, the cylinders are placed in the steam curing environment. This is seen in a couple of different places. Now, as I said, I'm going to quickly explain accelerated curing. The standard defines here in particular that when cylinders are going to be placed into a very hot environment, the cylinders now need to be heated with a bit of a ramp up. Can't be taken straight from casting and placed in 80 degrees heat water. They need to be raised. So if you expect the internal temperature of the concrete to get to a certain point and you're using a match temperature curing system, it's important the cylinders make it into that curing tank before the heat increases. They need to gain heat as the concrete element gains heat, not be shocked by placing in. Also, for warm or hot, there needs some amount of time outside to cool before demoulding. The other requirement here is that these are sealed cylinders. These are not just a cover. They actually need to be keeping the water out to prevent that influencing the concrete inside the mould. So if you're going to be using a match temperature curing system, it's important that you need to give some thought if they're being placed in immediately. How are we going to protect the unset concrete from the water? And if they're being placed in after a normal setting time, is that water going to be a suitable curing environment? Again, AS10 12.8 defines that it's a lime saturated water environment. So these things need to be considered as part of preparing for the systems. Now, finally, the samples need to be crushed. As part of that, the top surface, which was levelled but not left entirely smooth, needs to be allowed to be flat, plain and square. So commonly sulfur capping or grinding will be used. Grinding's proved to be an easier system for this, grinding plane to 0.05 of a millimetre, and the crushers may better represent the strength depending upon, again, how those samples have come together. Standard also defines the rate. So what's different with match temperature curing? So match temperature curing is where we're going to take the cylinder sample and place it inside something which is going to gain and lose temperature at the same rate as the real concrete element. In something like a steam curing environment, it's assumed that by placing the cylinders directly into the steam curing environment, they're going to cure the same way the concrete being cast in that environment does. If it's a water bath, if it's water curing and there's a water bath on the same line as the heated water travels in or travels out, placing cylinders into that water bath allows the water to match the temperature that the environment's curing at, but it doesn't capture the internal temperature. Now, another technique that I have seen used is where there are cores taken from the element after it's sort of gone through initial curing, or where plastic cylinder molds are placed inside that element and can then be popped out to give a ready-to-go cylinder heated by the concrete around it. Match temperature curing tanks instead try to capture the concrete's heat in an external environment. A temperature sensor is placed in the concrete, and whenever we're using a temperature sensor as a tool to assist us with early gauge strength, the placement of that temperature sensor is important. If there's a critical area where stresses are going to be greatest in the structure, or it's important that the sensor be placed to capture the strength gain of that area. And similarly, if it's worried that if you place a sensor internally and there's going to be in a bulk element, there's going to be more heat internally to that element than on the outside surfaces. So choice of sensor is going to come down to the engineer who understands roughly what the heat gain is going to be in that structure, and is going to place the sensors to capture the information they need. You'll see this again when we come to maturity. So the match temperature curing tanks, they capture this temperature, and they have a refrigeration plant to cool the concrete and a heating element to heat the concrete, and they're going to track along with that sensor. So as I mentioned when we were discussing curing earlier, that's still a cylinder sample being cured, so it needs to be protected from the water, and the water needs to be correctly set up to make proper use of a match temperature curing tank. You don't want to artificially reduce the strength of a cylinder sample because it wasn't cured properly out on site rather than back in the lab. So moving on to the in situ tests, I'll come back to the summary of techniques. So we see we've gone away from direct strength testing. The in situ tests typically rely upon relating an external factor to the compressive strength of the concrete. I'm going to discuss penetrometer testing, Schmidt hammer testing, and maturity measurements. So penetrometer testing and Schmidt hammer testing are relating a rebound or the penetration force required to place a needle into the concrete, so they don't directly capture the heat on the internal areas of the concrete. They're instead a measurement from the surface, which may be fine. It may be that we want to know the lower strength, so a surface measurement is very appropriate. Whereas with maturity measurement, we can again take a temperature sensor and place it internal to the concrete. So we're capturing strength at a point. Now the relationships are going to depend upon how well we take sample compressive strength tests and relate them back to our real concrete used on site. So the first point is, whenever we're doing a correlated method, you need to establish that relationship between a certain concrete mix and a certain technique of strength measurement. So this means that for where we're building custom curves, particularly Schmidt hammer testing and maturity testing, there needs to be quite a large test mix done to build the curve that is then used on site. Then finally, once we're out on site, we need to have the sensors installed or the tools to use out on site. That's where I place the equipment requirements. So Schmidt hammer testing. The Schmidt hammer testing looks at a surface hardness of the concrete using the principle of rebound. A sprung-loaded weight is allowed to strike a metal bar in contact with the concrete. This drives the bar into the concrete and returns some amount of the energy from that strike to the hammer. If we get a lot of energy returned, that's a harder material. If we lose a lot of energy, it's a softer material. The hammers will read out in units of R or Q, which is a dimensionless measure of energy returned. We take this measure of energy returned and we, based upon taking compressive strength tests, relate it back to a concrete strength. Schmidt hammers are used for testing new and old concrete, and often there will be a curve printed on the side of a Schmidt hammer, or the Silverschmidt models will report MPa from a number of built-in curves. Those curves are not really suitable for early age strength. We already don't have a relationship to a particular mix, and even more than that, we have a relationship to materials that are not Australian. Those are very often a European test of older concrete. So it's really critical to build your own curve if you're going to be using a Schmidt hammer for early age strength measurement out on site. And as I mentioned earlier, the Schmidt hammer is a surface measurement. This may well be fine if we wanted to get a relatively conservative view of the concrete strength. Precasters of panels and similar, a Schmidt hammer measurement can be quite good. It's not so thick an element that it's going to have a lot more heat inside than outside. And it's a useful quick tool you can use on a lot of elements around you without installing sensors or other preparation. So when we build a curve for a Schmidt hammer, the first step is to collect enough samples of differing strengths. If we cure 30 samples and break them all at 28 days, there may not be enough strength range. It's important that the breaks happen during the early low strength stages for an early age strength curve, and that we have enough cores to produce cores or cylinders to produce a full curve. Cores are not commonly used, but if they are, it's important to test the region that the core is being taken from before it's removed, and then use that to relate to the strength of the break. With cylinders, they do need to be held securely. If the sample slips or moves under the strike of the hammer, it's going to report a lower rebound value. So in a cradle, or commonly, a little bit of pressure can be applied in the machine to hold it firmly, the sample test taken, and then the compressive strength test completed. Finally, the relationships from a Schmidt hammer do have an inherent uncertainty. When we're striking the surface, there may be a surface inconsistency, or there may be some local variation in strengths over that surface area being tested. So we do want some form of safety factor. One useful way to do that is to use a lowest 10th percentile curve. The principle there is, if you look at my curve on the right, we have a line which represents the midpoint of those test results. If instead we map out a line that places most of our test results above the curve, we're going to have a more conservative strength relationship when we use that curve. Finally, once you've got this graph, we can read up from rebound results to get compressive strength results. Moving on to the pocket penetrometers or the shotcrete penetrometers, the penetrometer principle is essentially a needle with a known dimensions is pressed into the partially cured material. If the material has achieved a final set, the needle cannot penetrate into it, so this is very much only an early age strength measurement. The dimensions of these materials control how much force is required to press in, And by relating that force back to a compressive strength value, we have our measurement. In particular, the cement penetrometers may be used for grout testing or get an idea of when that grout's getting an initial set on. But we haven't built a curve. The scale for the penetrometers is written on the side there, 0 to 5 MPa. So we're not going to have the same quality of relationship when it's a built-in curve based upon rough material properties than when we take the time to build our own curve. And you can see the dimensions for two commonly used penetrometers in the text. Now, concrete maturities need a little bit more explanation. So, with concrete maturity, what we're trying to do is we want to take a temperature sensor, which is going to be placed out on site in the real concrete at a point of strength gain. And based upon that, we're going to relate the time that concrete has been curing at a certain temperature back to a gained strength. The first thing to do is that we need to look at which maturity index we use. There's a Nurse-Saul relationship or an Arenhus relationship. I'm going to explain them in the final section of this webinar, where I go deep into the ASTM standard. But in summary, one of them establishes a time temperature history. So this concrete element has been existing at 30 degrees for 5 hours, then 35 degrees for 6 hours, and they're coming into units of time and temperature, time multiplied by temperature. This value increases as the concrete remains and gains strength, and when it reaches a certain value, we know that based upon our established curve, which I'll talk about building in a second, what strength has been gained. The other relationship attempts to look at a equivalent age of concrete. So instead of looking in terms of a time degree centigrade unit, the unit is equivalent age. So if we've been curing this concrete in a standard curing condition, might be 23 degrees, might be 20 degrees, and it had been around for 50 hours at that curing environment, it would have an equivalent age of 50. Whereas if we go from a 20 degree age to a 40 degree age, and we cure for 50 hours, the equivalent age is now 100. More or less. The actual equations are in the final section, and there's more detail there, but that gives you the rough ideas of what these two indexes are used for. In either case, we watch the increase in index as time occurs, and that index will inherently take into account the temperature change in the material. Once a certain value is reached, we'll check that versus our strength relationship and read off a strength from the graphs. Now, the other key thing to be aware of with maturity is that it is used as an early age strength relationship. It's not a replacement for a cylinder strength. If you take a maturity reading system and you check a value after 20 days, 30 days, 40 days, there will be a continuing increase in strength of that sample. But even if the curve has been set up out to those higher strengths, the relationship is better earlier on in the curve. And there may be some other applications using similar techniques, strengths, but maturity as it's commonly used is a early age strength only tool. So the key relevant standards, the most commonly used one is ASTM C1074. Now this standard has actually been approved for some users by NATA, so it's possible to work with someone who's approved in the use of maturity to the ASTM standard. There also is an upcoming proposed recommended practice with in the CIA conference. So these are going to be interesting things to review in the coming months. So when we want to build a strength relationship, it's a large-scale batch, large-scale batch test mix. So we build maturity relationships for each type of concrete to be used. We will cast a large numbers of cylinders, at least 15, and we're going to embed our maturity sensors, which are logging the time history of the concrete, and they may be calculating one of the maturity indexes as well. And we are then going to break these cylinders at intervals. If we don't have a particular schedule, the standard recommends 1, 3, 7, 14 and 28 days, but the choice of when the samples are broken is going to depend upon when it's important that the strength be gained. So if we're concerned with really early strengths, the first 5, 10, 15 MPa of strength gain, there needs to be lots of breaks early on. Whereas if we're concerned with mid-age strength, then 1, 3, 7, 14, 28 may be more suitable. One of the critical things is these samples are cured as per a normal concrete sample. Maturity is a way to create a relationship based upon conventional curing environments. So that's 28, 23 degrees in lime water with 18 hours air curing first. Critical things, the instrumented samples must be cured the same way the concrete samples are. If they get colder or hotter than the samples that are going to be broken, they will no longer represent the maturity of those samples. So it's important that every mold be moved together at the same time as soon as possible. Similarly, if it's such a big batch of cylinders that they can't be cast at the lab in one go, the standard does mention that they should be cast batch 1, batch 2, and then one from each batch broken during the appropriate breaking times, the 1 day, 3 days, etc., or as required. The other key criteria of that standard is that the time interval where the temperature is logged is every 30 minutes at most. It could be less, it cannot be more. And I had a question before our seminar about looking at tensile strengths and and other strengths of concrete. It is possible to build a similar relationship with other kinds of samples. Similarly, if we look back at match temperature curing tanks, it's possible to cure other kinds of test samples in those tanks. So if your requirement is not to track compressive strength, but to track another parameter of concrete, these may be suitable because you can build multiple relationships using maturity, but a different strength test. Then, once we've got our curve built, we need to take measurements out on site. The sensors need to be cast into the concrete or placed into the concrete immediately after the concrete is poured. They need to be away from things that might take heat away from them. So if you have a large amount of steel reinforcing, the sensor needs to be a little proud of that, so it's not allowed to cool or heat more quickly by the change in heat of that steel. And when there's a parameter that needs to go into the sensors, there's a datum or activation energy parameter used by each of the maturity indexes, and the sensor hole that's internally, it needs to be entered correctly at the beginning. Otherwise the data will need to be adjusted afterwards. Now, the final thing about maturity on site is we need to monitor what it's doing. It may be that conventional early age breaks are compared to results from on-site, or it may be that when the early age cylinders are cast and are being used as backup or as another QA tool, that a maturity sensor is embedded into an additional cylinder which will travel with those site cylinders and be and so when they're broken, there will then be a maturity check at that point. Because if materials shift or the mix shifts over the life of the project, you don't want your curve to be out of date. The curve may need to be reworked if the materials change on site. So that completes the quick overview of the different test techniques. I'm going to go a little bit more into the ASTM standard for maturity, looking at the formulas used inside it. So the ASTM standard defines specifically the two maturity functions, that's the equations used. It defines, as I just showed you, the procedure to make a maturity relationship. It also defines the sort of instruments that can be placed out on site and the procedures, like I just mentioned again, on how to confirm the strength relationship is still useful when it was developed, say, a few months ago, and we've been delivering concrete to site, and is that maturity curve still valid? Now, it also mentions specifically limitations of the technique, and these are quite important. The technique assumes that concrete is continuously hydrating. if there is something that prevents the hydration of the concrete, very low temperatures, or lack of moisture, improper curing, a temperature measurement for maturity may not capture the real strength of the concrete, because if we've lost moisture and the concrete cannot gain hardness due to the loss of moisture, that relationship is now of concern. As it also does not take into account the effects of those early age strength gains on the final strength of the concrete. One reason why a 28-day cylinder should still be used. And the final thing is, it's the quality of the curve creation that is going to control the quality of the eventual maturity relationship and how it's used. So, the first method of calculating maturity is the temperature time factor. The temperature time factor assumes the strength development is a linear function of temperature. So if we increase the temperature, we get a corresponding increase in the speed of strength gain. The datum temperature attempts to capture when hydration would stop for that particular mix. And the calculation is that for each point, the temperature time factor relies upon the average concrete temperature during that time interval, minus the datum temperature multiplied by the time at that temperature. So fairly straightforward calculation. The equivalent age is the other maturity index used, and this assumes that the strength development obeys the Arrhenius equation. Now, what does that mean? The Arrhenius equation is a formula for the temperature dependence of a reaction rate. So if we place two chemicals and they're going to have a endothermic or exothermic reaction, and we place that into a water bath, and we maintain the temperature of that reaction at a cold temperature or a hot temperature, this equation is a means to model the rate of that chemical reaction occurring. Critical to the Arrhenius equation is this idea of activation energy. There is a point where chemical reactions will no longer progress because there's not enough energy in the system. So this is captured by the Q factor in the equation. Activation energy serves the same role as a datum temperature. It's a way to indicate in the equation when hydration would stop happening because there's not enough energy in the system. The other key point of this calculation is that a specified temperature is recorded, as well as the average temperature. This specified temperature is what the equivalent age relates to, a amount of time spent at 20 degrees or 23 degrees. So that's the particular details of the functions described in the ASTM standard. I'm now just going to call out a few quick details on some Australian standards that do attempt to better capture early age strength. So with the curing of test cylinders by specification 820, which is a main road WA specification, it has indication of co-location in a steam curing environment, and that they are then transported out to the lab. For the Roads and Maritime Services R82 lean mix convex, this is a standard used for a cement road base, where they do not want to use cylinder strengths for testing. They don't want to cast a sample and break it, though they may use cylinder samples during trial mix testing. Instead, they are specifying that cores be taken from this road base and placed out. It defines that two cores should be taken and broken, and then they should have a fairly even strength. If there's a difference of 1 MPa between the break of both samples, a third one should be taken. It also indicates that a third should be taken if the strengths measured are less than 4.5 MPa. And the coring samples, these samples are taken according to the procedure in AS10 12.14, but they do make some modifications. So this is a requirement of your project. It's important to review the R82 requirements and the AS10 12.14 requirements. Finally, VicRoads provides direct guidance on maturity, not so much on the techniques that are used, but on how to make your case for the use of maturity on a project. And this is useful guidance whenever presenting maturity as part of a project. So it defines that various types of maturity testing may be used to determine early age Insitu strength development for formwork removal, precast unit lifting, or early stressing, and that they expect that the documentation provides a detailed explanation of what is being done, along with evidence of its previous use, including how accurate the relationships were on site. So this is the evidence that's required to be presented. And similarly, VicRoads does specify that test cylinders be cured in a steam curing environment cylinderly. So coming back to a quick summary of what we've discussed, I've discussed two particular early age strength measurements. The use of direct strength measurement by breaking cores, and the use of correlated methods such as Schmidt hammer testing or maturity measurement. I've attempted to indicate that the cores take a direct strength, but if you break a core, you can't break it again, whereas the correlated measurements offer the ability to check strength gain and then check again. I've tried to explain why the strength relationships are of a good or poor quality, in particular that with the ability of care that can be taken to ensure a good relationship between strength gain and the correlated method. I've also tried to explain the equipment required. So for example, with co-location, all that's required is that the cylinders which are being cast anyway are placed in a suitable environment following the temperature. Whereas with something like a match temperature curing system, there is additional curing tanks required. When it comes down to the correlated methods, there's less equipment required on site, but there is the requirement to use sensors or have instruments used for that measurement there. I've also tried to go through the specific setup requirements, where care must be taken to ensure the relationships being used are built for the concrete mix. I did have a few questions before, and I've got one question on the live chat now. The question from the Orange A Anonymous is that, does the Arenas also have a maximum rate where molecules will start getting in the way of each other? There is a non-standardized method of using a different Arenas equation, because the one used during the standard ASTM maturity method is one version of the equation. There's others which will take into account different activation energies to better represent, again, better model the maturity gain, and which is information. So the more we do to improve our maturity gain strength relationship, the better the quality of our on-site results are going to be. I've also had a question on, is cracking due to a lack of, because cracking is due to a lack of tensile strength in concrete, can these early age strength tests provide a measure of tensile strength at an early age? They also asked about what is the relationship between compressive strength and tensile strength at an early age. Now, I'm afraid I can't talk in detail about the relationship between compressive strength and tensile strength. I do know that there are some guidelines people keep in mind, and there has been some research done there. I don't have that information to hand. But as I mentioned, you can cure in a match temperature environment samples used for tensile strength testing or flexural strength testing and break them. So that's one way to take into account different measures of strength. And it's also mentioned in the ASTM Standard that other tests can be conducted when creating that curve, creating a relationship to a different form of strength for that maturity. This questioner also asked about the use of the maturity method for predicting the strength development of concrete. In particular, the equipment and controls needed during creating that curve. So some of the key criteria when you're making the curve in the lab is that there is a minimum of 2 redundant temperature sensors, and you'd be very wise when measuring on site, if you wish to capture it, to use a very durable sensor or a suitably redundant sensor. So a durable sensor where the cable or the equipment is not going to break due to vibration and load, or if you're installing multiple temperature sensors, that's also a form of backing up and ensuring that information is there. The other information in the lab is that you need to record every parameter. You need to know which mix was done and take the same care you would with any other testing situation. The final question I had, so I just need to quickly look this one up, was about 2 and 3 day stripping and steam curing is common. If we field cure at these conditions, we do not meet the standard requirements. Steam especially is a regular deviation from the method and endorsing reports. Is lobbying Australian standards an option to change the field curing standard to reflect consumer needs? So I don't sit on standard boards, but there is always the potential to get involved in the creation of better Australian standards and international standards. In particular, the question of 2 and 3 day stripping is common. And of course, with the field curing, it may be possible to improve it, but if it's not in a standard, standards do not have the force of legislation. They are a recommended best practice. What they are not is a legislated required practice. So the agreement is instead between the client and the people completing that work. So if you wish to use an alternate means of measuring strength or curing samples, it's very important that be raised at the design stage of that project or the tendering stage of that project as an option. And again, so that's the questions I've had beforehand. If you've got any other questions, we have the live chat on the right hand. I'm very happy to answer anything specific to maturity, or if you've got some general questions on non-destructive testing or other areas, I'm very happy to talk about that as well. But thank you very much for joining us for our second webinar. I really enjoy doing these, and I'm hoping to present at least one more for you this year. I'm also going to be helping out a lot with our upcoming training events, so keep an eye out for the specific invitations for your state to our training event with ProSec, and do come to our stands at the upcoming conferences. We're going to have a lot of exciting equipment there, and you can always ask questions to me or any of our staff directly as well. Thank you very much for joining us. As I said, I'll wait for a few other questions if anyone would like to ask any. Okay, I haven't seen any more questions come through, so thanks again for joining us. I'm going to close the stream now, but if you do have anything I can do to help out, please do call your local staff member at PCTE. We all know a great deal about these different test techniques, and in many cases, if we don't know ourselves, we definitely know the people to ask out in the industry. Thanks so much for your time.